Hey, in this tutorial we are going to learn the syntax of the GLSL ES language and then wrap up with some examples to better understand some of the concepts that we are going to see. So what is GLSL? GLSL stands for OpenGL Shading Language. In a nutshell, it is a programming language through which a web application can communicate with the graphics card in order to display 2D and 3D stuff on the browser. That being said, if you want to learn more about the subject, I made a video in which I explained the relationship between OpenGL, GLSL, WebGL, and 3D libraries like Three.js and Babylon.js, link in the description. Comments in this language work the exact same way they do in many other programming languages. So, if the comment doesn't exceed one line, we type // and then the comment. On the other hand, if it's a multi-line comment, we open the space dedicated to the comment with a / and close it with the opposite. Again, same as JavaScript, for instance, we have variables in which we store information. Notice though that in GLSL we have to specify the type of the data to be stored in the variable beforehand. We also have constants, which are variables that need to be initialized and can't be updated. And again, the only difference between constants in GLSL and JavaScript is the data type. In GLSL we have three basic types, which are int, float, and boolean. And yes, I didn't mention characters and strings because they don't exist in this language. Having said that, once we assign a type to a variable, we can't set a value of another type to it. For example, we can't put a float in an int variable and vice versa. The only way to do that is to convert that value using a conversion function, and here are some examples. Int true returns 1, float 2 returns 2.0, float false returns 0.0. Then of course we have a variety of operators to apply different kinds of operations like addition, subtraction, division, etc. The other types we have are vectors and matrices. These two types are similar to objects in object-oriented languages, so they are basically entities that are composed of basic types. Something I need to mention here is that in this tutorial I'll be focusing only on the programming side. However, it is highly recommended to have some basic knowledge of maths to understand the mathematical representation of what we are going to see. Speaking of maths, a great resource I suggest you to look at is the Math for Game Devs playlist at Freya Holmér's channel. She did an amazing job to cover some themes such as the definition of vectors and matrices, vector normalization, interpolation, Bezier curves, and many other topics. Now let's start with vectors. We actually have three categories of vectors, if you will. Float vectors labeled as vec, int vectors labeled as ivec, and boolean vectors labeled as bvec. So basically, each one of these categories is composed of a certain number of elements that belong to one of the basic types that we've seen earlier. The digit refers to the number of elements each vector is composed of. For instance, a vec2 variable represents a vector composed of 2 floats. bvec4 is a vector composed of 4 booleans. Another way of creating a vector when its components have the same value is to specify that value only once. We can also set the values from another vector as long as it is equal or bigger than the one we are creating. So here vecd will have the two first values from vecc. Furthermore, we can use more than one vector values to create a new one. Now that we learned how to create vector variables, let's see how to set and get data from their components. To access the first component, we need to specify the variable name followed by a period, then x, r, or s. To access the second component, we need to do the same but with y, g, or t. To access the third component, we need to type z, b, or p. To access the fourth component, we need to type w, a, or q. As you see, we have a variety of notations that do the same thing, but you should use the right one depending on the context. So if you're dealing with vertices positions, it would make more sense to use x, y, and z. If you're working with colors, it would make more sense to use R, G, and B, and S, T, and P if you're working with textures. Keep in mind that we can access more than one component at the same time, so here we can create a new vector which components are taken from the first and third components of another vector. Another thing to mention is that we have the ability to repeat and take values in a different order. So repeating R here will create a vec3 which components are all taken from the first component of vect A, and here vict components are 3 in 1, which represent the third and first components of vict A. Quite similar to vectors, a matrix is composed of a certain number of floats, so we can have mat2, mat3, and mat4 matrices. That said, unlike vectors, a matrix can have different types of values at the same time, so we can have a mat2 with 2 ints and 2 booleans, for instance. However, those values will end up automatically converted into floats. The elements of a matrix are set in a column major order, so to create this matrix with code, it must be typed this way. To access a matrix components, we can use the brackets notation. M0, for example, creates a vector out of the first column of the matrix. M22 sets the last value of the matrix to 100. Furthermore, we can combine the dot notation that we use to get and set the values of a vector with the brackets notation, and here is an example. Mat B0y gives us access to the second component of the first column. We can apply a variety of operations on vectors and matrices like we do with the other types, so we can add, subtract, multiply, etc. Another type of variables we have in GLSL is sampler. There is sampler2d, which is what you're going to use most of the time, and sampler cube. In short, a sampler is a variable in which we store an image data. Same as other programming languages, we have arrays to store collections of data. To create an array, we need to specify the type and also the number of its element beforehand. So 7 here doesn't mean we are initializing the array with 7, it rather means that the array could take 7 elements. That said, to access an element we need to use the bracket notation pretty much the same way we do in C or JavaScript. Along with the different types of variables that we've seen, we have the ability to create our own types. To do that, we need to use the keyword struct followed by a name and a couple of opening and closing curly braces. Then we have to specify what are the components of our structure, aka our custom type. So that's like the skeleton of our type. To create a variable of that type, we simply do it the same way we do with other variable types. Now, to access the components of the variable, whether to get or set their values, we have to use the dot notation like we did with vectors. Again, same as the other languages, GLSL has control flow statements, so we have if-else statements and for loops. Then we have functions. A function in GLSL, like a variable, should have a type, so if it returns something, the type of the function should have the same type of the returned value. On the other hand, if it doesn't return anything, the function's type must be set to void. We also have to specify the type of the parameters of a function. Now, if you want to create and call a function, the order matters, which means that we need to create the function first, then call it. However, we can do something to break this rule. To do that, we need to set what it's called the prototype of the function at the top. A prototype is basically the definition of the function without its body. Then we can call the function and set its full definition right at the bottom of the code base. GLSL is actually rich with built-in functions, so make sure to have a look at shaderific.com where you will find a brief documentation of any built-in function that you might need. I'll leave you the link in the description below. There are 4 storage qualifiers. We've seen one of them earlier, which is const. Then we have attribute, uniform, and varying. I actually think it would be easier for you to fully understand the purpose of these qualifiers if you learn a little bit of pure WebGL, but still, here's a brief explanation. Attribute and uniform variables are variables that receive data from the outside of the GLSL code, from the JavaScript side of the application code more precisely. Now, the difference between the two is that an attribute variable holds data that is different from a vertex to another one. A vertex is a point, by the way, so positions of vertices that form a triangle, for example, should be passed as attributes because each vertex has a different pair of coordinates. Time, on the other hand, should be passed as a uniform variable because a set of placed vertices share the same time. 5 seconds passed for a vertex, for example, are 5 seconds for the other vertices as well. They can't be less or more. Another difference between attributes and uniforms is that the number of attribute variables allowed is less than the number of uniforms. Also, attribute variables can be used only in the vertex shader, while uniforms are allowed in both the vertex and fragment shaders, We'll get into shaders later on, so don't worry. Varying variables, on the other hand, are used to transfer data from the vertex shader to the fragment shader. That's it. Precision qualifiers represent a way to optimize the resource consumption, the memory usage more precisely. There are three precision qualifiers, which are low P, medium P, and high P. Low P being the less consuming. However, you need to carefully choose the right precision, since a lower one sometimes can give incorrect results. To set the precision of a variable, we just need to start the declaration with the wanted precision qualifier, or we can set a precision for an entire type of variables by typing the keyword precision followed by the precision qualifier, then the type. Now that we've seen the syntax of GLSL, let's talk about shaders. Simply put, a shader is a small program that is written in GLSL. Having said that, we have two types of shaders, the vertex shader and the fragment shader. As you may know, every object in 3D, whether it's a point, a text, a shape, or a 3D model, is composed of a number of vertices. That said, the role of a vertex shader is to take care of positioning every vertex composing that mesh in the scene. The code of a vertex shader must be typed within a function named main. Furthermore, this function will be executed as many times as the number of vertices that compose the mesh. So for example, if you create an object that has 500 vertex, the vertex shader will execute this main function 500 times to put every one of them at the right position. Now within this main function we must set a value to the built-in variable GL position, and as its name suggests, it's where each vertex coordinates are stored. The value of GL position here depends on the 3D library you're using. In Three.js you'll have this line where projection matrix, model view matrix, and position are Three.js built-in variables. The first two are related to the camera view in the overall calculation of the final value passed to GL position, and the third one is where the initial coordinates of one vertex are stored. Again, this may be different if you're working with a different library like Babylon.js or Pixie.js. Now that we have at least an idea of what a vertex shader is, let's talk about the fragment shader. Essentially, the role of a fragment shader is to colorize vertices in the meshes they form after they get positioned by the vertex shader. That said, the colorization process goes through a handful of steps, but as a beginner all you need to know is that the fragment shader decomposes the mesh that is created out of the vertices placed by the vertex shader into small fragments, then proceeds to colorize them. Now, same as the vertex shader, a fragment shader code must be set within the body of a main function, in which we also need to specify a special built-in variable which name is GLFragColor. And as its name suggests, GLFragColor is where the color of one fragment is stored. Each one of this vec4 variable represents a color channel, so the first value represents the red channel, the second represents the green channel, the third one represents the blue channel, and the fourth represents the alpha channel. Bear in mind though that the values of these components start from 0 and end at 1, so every negative value is same as 0, and every value that exceeds 1 is equivalent to 1. Let's practice with some examples. As you can see, I have a very basic template in which I loaded an image that I'll need for the last example, and a 10 by 10 plane with 30 width and height segments. We also have the shader material with the wireframe mode set to true to display the vertices that compose the plane. And I also have the vertex and fragment shaders already linked to the material. If you don't understand something from this template, you need to watch my Three.js guide where I have explained every single part of it, link in the description. Now let's use the vertex shader to update the positions of the vertices that compose this plane. To do that, we simply need to update the value of this position variable, which is of type vec3 since it has the x, y, and z positions of a vertex, so I'll just apply the math function sign here. As you see, the vertices of the plane now form a sort of a pattern. Let's try to apply another math function, and I'll use tan this time, which stands for tangent. We can also animate the shape by changing the coordinates of the vertices over time. The problem though is that unlike JavaScript, we don't have something like the date class to get the current time. So what we are going to do is to pass the time from JavaScript to the Vertex shader using a uniform variable, which is one of the 4 storage qualifiers that I explained earlier if you remember. Back to the JavaScript code, let's create an object in which we will set every uniform variable that we are going to use in the Vertex and Fragment shaders. Every property that belongs to this object represents a uniform variable. That said, the properties are objects and each one of them can have a type property, which is optional but it is recommended. So here I'll pass the time as a float variable, thus the f as type. In addition to that, it must have a value property that contains the value we want to pass to the shader. Next, we need to pass the uniforms object to the uniforms property in the shader material configuration object, and here we can go the ES6 way since our object has the same name as the key of the property. Then we need to update the value with the elapsed time from the moment the page was loaded in the browser. To do that, we'll need to create a clock and then update uTime with the value returned by getElapsedTime from the clock instance, and that's it for the JavaScript part. Now, in the Vertex shader, we need to create the uniform variable which name must be the same as the property name in the uniforms object. That done, we can use the uTime variable to change the x position of the vertices, for example. So here I'll create a variable which value is calculated out of the time, the x position and the y position of each of the plane vertices. Then I'll create another vec3 variable that represents the new coordinates of a vertex. So here we are basically changing the x position while preserving the y and z positions. And then I'll replace the initial position with the new position. And there we go, you can see how a short random math equation applied to the x position of a plane vertices made such a big change to its shape. Let's bring back the plane to its original form and turn off the wireframe mode. That done, let's change the color of the plane using the Fragment shader. So, as I said earlier, the GL frag color value is a vec4 which components represent the RGBA values of one fragment's color. Therefore, altering these values will result in a color changement. We can also create a color animation, and again, talking about animation means time, so same as we did in the Vertex shader, we are going to create a uniform variable to get the time and use it to make the animation. Furthermore, we can change the color of an object depending on where it stands in the scene. For example, we can make the plane look greenier the more it is close to the right edge of the screen, and darker the closer it is to the left edge. The problem is that in GLSL we don't have a way to get the resolution of the screen in order to achieve the gradient color. That said, the solution is to provide the information through a uniform variable from JavaScript, so let's do that. We'll call this variable uResolution, and the value is going to be a vector2 holding the width and height of the window. Something to mention here is that I have seen some examples on the internet where developers add this optional portion of code. Looking at the MDN, it seems that it is useful to show better results on high DPI screens. Next, we are going to create the uniform variable and use the X component to create the green gradient. Nothing has changed, and that's because we are passing values that exceeds 1. At the middle of the screen, for example, U resolution X is equal to 960, which is equivalent to 1. In other words, the G component of the GL frag color will be set to 1 no matter where the plane is, since we are passing values that are bigger than 1. The solution to that is to convert the values from the document coordinate system to the fragment shader coordinate system, which starts from 0 and ends at 1, and to do that we simply need to divide the later by the former one. So here, GL fragCoord is a GLSL built-in variable that holds the position of the current fragment in the fragment shader coordinate system. Then we need to replace the U resolution variable with st. Now, as you can see, the closer the plane is to the right side, the greenier it gets, and the closer it is to the left, the darker it gets. That done, we can also create another color animation, not with time, but with the mouse position this time. Again, GLSL doesn't have a function to track the mouse position, so we are going to pass this information through a vector from the JavaScript side to the fragment shader with a uniform variable. We'll convert the mouse position coordinates in JavaScript this time. And now we'll use the data from the UMouse uniform to set the green and blue channels. Same as colorization, dealing with images and texture mapping is done using the fragment shader because images are nothing but a collection of colors after all. Once again, we'll need to use a uniform variable to pass an image data to the fragment shader. Here we have the image set as a sampler 2D variable. To use it to colorize the plane, we need to convert it into a texture first by calling the texture 2D function. The first argument must be the sampler 2D variable, and the second one represents the space where the image should appear. I'll use st here, which means the entire scene. Now we can colorize the plane by taking the colors from the image, so here for instance we can take the green color from the image. We can also take the other two channels, which will end up displaying the image as it is on the plane. And again, we can create some effect using time, for example. Now, as you can see, the plane is taking only a part of the image, and that's because we set the entire scene as the dedicated surface on which the image should be mapped. That being said, what if we want the image to be fully displayed on the plane? To do that, we need to set the surface of the plane as the second argument of the texture 2D function. The bad news though is that we don't have such a built-in variable that contains that information in the fragment shader. The good news, however, is that Three.js provides an attribute to the vertex shader under the name of UV, which means that all we need to do is to pass the value of that variable from the vertex shader to the fragment shader. If you remember, I've talked about such a variable type earlier in the video. Yes, you're right, we need to use the variant storage qualifier. So first, we need to create a variant vec2 variable in the vertex shader. Next, we need to create another variant variable that must have the same identifier as the one created in the vertex shader. And finally, we need to pass that variable as the second argument of the texture2d function, and that's it. Last words before I finish the video. I know that some parts seem a bit complicated, but trust me, once you practice a little bit, all will fall into place. I actually think that the real struggle with GLSL is how to transform an idea into an applicable set of math functions in order to apply a certain effect or animation, which I think requires a good ability to visualize mathematical formulas and a lot of practice, of course. With that being said, make sure to like and subscribe, and I will see you in the next video.